So, let's go ahead and get started. Let's talk about Coulomb's law and the beginning of electricity and electric fields and electric forces. So, first thing, what exactly is Coulomb's law? Can anyone explain to me what Coulomb's law is? Coulomb's law from your formula sheet, and then also what exactly each part of it means. Anyone want to type it out in session text, or you got it, Kevin? Kevin, are you trying to talk right now? You unmuted the mic, but I'm not hearing anything. All right. Well, Coulomb's law. You tried? Okay. Yeah, I can't hear you. But let's keep going. So Coulomb's law, right? It's the first thing on Unit 5 from your formula sheet. It's F, with your little vector 1, 2 is equal to K Q1 Q2 over R12 squared R12 hat. So what exactly does each part of this Coulomb's law mean? First of all, what are Q1 and Q2?
Charges.
Yep, so it's two charges we have. Let's say we'll call that, and we'll put them in these two spots in space. So we have Q1 and Q2. And then R12, what exactly is that?
Which direction?
It's the direction, or like the distance between them, you mean?
I thought you meant the other R12, yeah.
Yep, so R12 without the hat is the actual distance between them. So we have R12. And then R12 hat, you said, was the direction?
Yeah.
Yep, so essentially this is a unit vector to essentially help us describe what direction the force is in. So for example, we have an XY plane. X hat direction would be obviously in the X direction, Y hat, and R hat direction means it's directly from one charge to the other, and vice versa. And so using this and then the constant K, you can calculate the forces acting between 2 point charges. We can essentially calculate the force on 1 point charge due to another. And then, does anyone remember Newton's laws from back in Physics 121? What's Newton's third law? And remember Newton's third law. Also, wouldn't hurt to remember Newton's second law as well, since you'll be using it.
For every action, there's an equal and opposite reaction, right?
Exactly. So, if Q1 is exerting a force on Q2, that means that the same force is going to be exerted back on Q1 in the opposite direction. So, if the force on Q2 is over here to the right, there's going to be an equal force on Q1 to the left. So, and one more thing we want to understand is what exactly are protons and neutrons, and we want to know what their mass and what their charge is and whatnot. So what are protons and neutrons? Once again, everything you need is going to be on your equation sheet.
What do you mean, what are they?
What do you know, what exactly protons and neutrons are in the context of this class? I'm not asking for deep dive quantum mechanics here.
I guess not. No.
Anyone want to help divvy it out?
Try
Oh, I hear you. I hear you now.
Oh, okay.
Hell yeah.
I think the term is subatomic particles, and basically they have different charges. So an
Mm-hmm.
electron, wait, no, a proton would be a positively charged particle in the nucleus of the
Mm-hmm.
atom.
And do you know what that
Along
charge?
with
Do you know what that charge would be? Like, what's the
uh,
value of the charge in SI units?
I don't remember. Sorry. Um,
Isn't it like 1.6 or something?
Yep, it's 1.6 times 10 to the minus 19 coulombs. It's right there on the formula sheet. So,
Yep.
so proton plus E, 1.6, 10 to the minus 19 coulombs. And what about the electron? What's the charge of the electron?
It's the same.
The same, it was the same magnitude, right? But it's
Yeah.
opposite
Oh, it's
inside.
yeah.
Yep, so an electron, the charge is the same, but opposite, it's minus E. And the other thing we want to know is what are the masses of these two particles? What's the mass of a proton and the mass of an electron? It's not on your formula sheet, but still highly recommend write it down somewhere and memorize them. If you've taken Chem 101, it might already be ingrained in your head. Or I don't know if you'd worry about it too much in Chem 101.
Isn't it like Avogadro's number or whatever?
Not quite.
1.6 something.
You're on the right track.
I remember.
It's,
I
it's,
remember.
it's 1.67. So for a proton, the mass is 1.67. And does anyone know what magnitude it's on? So like for the charge is 10 to the minus 19. Does anyone know what magnitude the mass of the proton is on? In terms of kilograms? It's actually 10 to the minus 27. It's extremely small. 10 to the minus 27 kilograms. And what about an electron? Does anyone know what the mass of an electron is? Is it the same as a proton?
I know that it isn't the same. Like they're much smaller.
Yep, much smaller. Does anyone know about how much smaller? It's about 1,000 times smaller. Nut value is, you guys can Google it, it's about 9.1 times 10 to the minus 31 kilograms. So that's basically most of the information that you'll need in order to do most of the problems you'll see in this unit. Honestly, most of the time he'll give you the masses of whatever charges you're using. He won't just say proton or electron or whatnot. He'll give you masses, he'll give you charges, and you'll be able to calculate stuff. So let's go ahead and hop into an example problem. So we're going to go ahead and place a proton and an electron 1 nanometer apart, and we'll call it, the proton's at the origin, so 0, 0. Let's go ahead and draw an axis. So we have our proton, call the proton blue. A proton here at the origin. And we'll say the electron is 1 nanometer away here. 1 nanometer. So we want to know what's going to be the force acting on the proton and the force acting on the electron. And then how are these forces related to one another? Let's go ahead and do parts A through C. Take like 5 minutes, and we'll come back and talk about it. All right, so let's go ahead and talk through it. So we are given the locations of the proton and the electron, and we want to go ahead and calculate the forces acting on each of them. So first of all, how do we calculate the force acting on the proton due to the electron? We can use Coulomb's law, right? So how exactly do we use Coulomb's law to do that?
We would plug in the charges for the electron and the proton,
Mm-hmm.
and then we would use the constant and the radius of 1 nanometer for the R.
Yep, exactly. So let's go ahead. We can plug everything in and get an actual magnitude. So the force acting on the proton, we'll just call it F1 for now, is equal to our constant K times Q1, Q2 over R squared, which we go ahead and plug everything in. We know the charges. It's plus and minus 1.6 times 10 to the minus 19. We know our R is 1 nanometer, and we'll have to convert that to SI units. We'll convert it to meters, square it. Do we know what the value for K is, our constant K?
1 times 10 to the 9, I think.
Not 1 times 10 to the 9.
Wait, what is it then? Something that times 10 to the 9. I forget. I just did that. I can't remember the first
You're
number.
pretty close. Yep, Zach's got it. 9 times 10 to the 9.
There it is.
Yep, so plug and putting our value for K, 9 times 10 to the 9, times our charges, which they're both 1.6 times 10 to the minus 19 coulombs, and I'm just going to go ahead and square that. We're just worried about the magnitude here. We're not going to worry about plus or minus. That's close enough to 0. That's going to say 0. And we are then going to divide by our R, which is, so it was 1 nanometer times 10 to the minus 9 to convert it to meters squared. And we get a magnitude of about 2.3 times 10 to the minus 10. It says we use SI units for everything. What's the SI unit for force?
Newton.
Yep, exactly, newtons. That's a pretty small force. But so we have our force calculated, and now we have to think about, we have the magnitude, now we have to think about what direction is the force going to be in on the proton. Because this is what I highly recommend all the time. Don't worry about plus signs and minus signs and whatnot when you're calculating stuff. Just plug in the magnitudes, and then at the end, go ahead and think, okay, what direction is this force actually going to be in? So we have our proton here, and the force is coming onto the proton because of the electron. Now, what does that mean about the direction of the force?
Can you repeat that?
So the force on the proton is incident on the proton because of the electron. So what does that mean about the direction of the force? Now, what do opposite charges do?
Attract.
Yep, exactly. Opposite charges attract. So our force on the proton is going to be towards the electron, right? So we have F1 on the proton towards the electron. Right? Nice and easy. We calculate the magnitude.
But you asked for the force acting on the proton, not on the electron, right?
Yeah, this is our proton here at the origin.
Right, wouldn't it be the other way around since it's acting on, I guess?
It's towards, the force is acting on the proton, and it's pulling it towards the electron.
Oh, okay.
Yep, the arrow represents the direction that the particle would travel.
Okay.
The 10 to the minus 9 was to convert from nanometers to meters, Zach. Is it Zach or Zachary? Which do you prefer? I'm just going to go with Zach as my default, because less syllables. Alright, sweet. But yeah, so 979 to convert from nanometers to meters. And our direction is going to be to the right towards the electron. Now, what about the force acting on the electron? First, let's think the magnitude. What's the magnitude of the force on the electron going to be? Is it going to be the same thing? Is it going to be larger? Is it going to be smaller?
What was that? The opposite force would be the same.
It's going to be the exact same. Yep, the exact same magnitude.
Yep.
And once again, opposites attract. So F2 equals same. And once again, opposites attract. So our force is going to be on the electron towards the proton. They're equal and opposite forces, right? Newton's third law. And that's sort of how these forces are related. It's the same exact force and magnitude, and they're acting in opposite directions. They're pulling the particles towards one another. Or if they were the same charged particle, it'd be pushing them away. So now let's go ahead and calculate the acceleration of both of our two molecules. So we want to calculate the acceleration of the proton and the acceleration of the electron. Let's take 3 minutes, then we'll talk about it. Welcome, welcome. We're going over parts D and E right now. Taking about 3 minutes, then we're going over it. Also, if anyone here hasn't already put their campus ID in the attendance form, if you could do that, that'd be greatly appreciated. Thank you. All right, so we've gone ahead and calculated our forces acting on our two particles. Now we want to go ahead and calculate the acceleration of each of our two particles. So how do we calculate the acceleration of something if we have already got the force? Throw it back to physics 121.
If you have the force, you would divide by the mass.
Exactly. It's Newton's second law. Oh, let me do this in black. The force is equal to the mass. The force on a particle is equal to the mass of the particle times its acceleration. So then to get the acceleration, we just divide the force by the mass. So what is our masses of our two particles again? Like the mass of our proton first?
Proton is 1.67 times 10 to the negative 27.
Yep, exactly. So we go ahead and divide 1.67 times 10 to the minus 27. We get a really high acceleration. It's like 1.4 times 10 to the 17. 1.4 times 10 to the 17. And what's the SI units for acceleration? We've kept everything in SI units up to this point. SI units for acceleration, if anyone remembers from Physics 121.
SI would still be meters per second.
Meters per second.
Squared.
Yep, exactly. Meters per second squared. And now for the acceleration of the electron, what's the mass of the electron? So divide by the mass of the proton to get 1.4 times 10 to the 17. And then our mass of our electron is, if anyone remembers, what is it again?
9.1 times 10 to the negative 31.
Yep, about 9.1 times 10 to the minus 31. So we get an acceleration of about 2.5 times 10 to the, I'm going to assume it's 20. Let me just double check. 10 to the 20. Once again, meters per second squared. Massive accelerations here. So, does anyone have any questions about this so far? We're able to use Coulomb's law to calculate the forces acting on two particles, and then we just applied basic Newton's second law from back in Physics 121 to calculate the acceleration. Any questions about this? All right. So let's go ahead and do the last part here. We're going to place an alpha particle, which an alpha particle is basically, it's a helium nucleus, so it's going to be two, I want blue here. So it's two protons along with two neutrons. And so that's what our alpha particle is. If you end up taking any upper level physics classes, you'll hear a lot about them. And so we want to go ahead and place our alpha particle at a point 2, -2 nanometers. So 2, -2, so it's somewhere 1, 2, somewhere down here, our alpha particle. And want to go ahead and calculate the acceleration of the alpha particle due to the proton and the electron. And now to do that, we're probably also going to want to calculate the force on it, right? So, one thing before I let you guys work on it, they don't know what the mass of our alpha particle would be if it's 2 protons and 2 neutrons. Or first of all, what's the mass of a neutron? Is it the same thing as the mass of a proton? Is it slightly heavier?
It's the same mass as a proton.
Yep, exactly. Or technically it's not, but no one cares about the 0.01 times 10 to the minus 27 kilos. It's the same mass. So that means if we have 2 protons and 2 neutrons, our mass is equal to 4. The mass of 4 protons, or if we want to multiply it, it's like what? 6 times 10 to the minus 27, roundabouts there. So let's go ahead and give you all, like, say 8 minutes. Let's say 10 minutes. So we want to go ahead and calculate the force on the alpha particle as well as the acceleration on it. And not only that, we want to know what direction is that force going to be in. So let's break it down into x and y components. So we want to find the x and y component of the force and the acceleration acting on our alpha particle. Redraw the picture here. So we're going to have our proton here as the origin, and we have our electron here, and we have our alpha particle down here. And so we want to be able to go ahead and calculate the force acting on the alpha particle as well as the acceleration and maybe a direction as well. So break it down into x and y components. So first thing, what's the easiest way to think about, breaking down forces from multiple particles? I'd say the easiest way is to completely ignore one of the 2 particles first, and so essentially calculate the forces from each particle individually and then add them together at the end. So let's just go ahead and ignore our electron and only look at our proton here. So we want to go ahead and figure out what is the force acting on our alpha particle due to our proton. So we want to go ahead and use, what law are we going to use to calculate this force?
So Coulomb's.
Yep, Coulomb's law. So we have F is equal to k q1 q2 over r squared. We're just going to calculate the magnitude initially. So we go ahead and calculate it. What are our two q's here for we have our alpha particle, our proton, and our electron. So we're talking about the proton and the alpha particle. What are our two q's here?
We have 1.6 times 10 to the 19th for the first one. I mean the proton.
Yep.
And the other one is going to be positive too. It'll be, I guess, twice as much.
Yep, exactly.
Yeah.
Yep, twice
So it'll
the
be,
charge.
3.2.
Yep, exactly. So we have our 1.6 times 10 to the minus 19. That's Q1 up here. Q2 is our 3.2 times 10 to the minus 19, divided by our distance r here. So you want to know how we would calculate that distance here? Remember, this distance is 1 nanometer. And so this would be 2 nanometers because it's minus 2. And along here, it's plus 2. So we're at 2, negative 2. So how do we calculate this distance across the diagonal?
You'd use Pythagoreans, and you got root of 8.
Yep, root 8. And that's in nanometers. Divided by, we'll call it 8 nanometers. And then we have to also, because it's nanometers, we have to have our 10 to the minus 9 to convert, and then square it. 10 to the, call it 10 to the minus 18. It's the same thing as if we did root 8 times 10 to the minus 9 squared. 8 times 10 to the minus 18. And then our constant k, which is, once again, 9 times 10 to the 9. And so we calculate our force. So F, we'll call it Fp. The magnitude of Fp is going to be 5.76 times 10 to the minus 11 newtons. And what direction is that force going to be acting in?
It would be towards the, well, outward. So like the proton would experience force towards the second quadrant, and then the alpha particle would experience a force down and to the right.
Yep, down and to the right. We're just worried about the forces on the alpha particle right now.
Yep.
So, but yeah, exactly right. The force on the proton would be up and to the left. The force on the alpha particle is going to be down and to the right. And what's the angle here? What is this, let's say this angle with respect to the x-axis of the force from the proton? That's exactly 2, 2.
It's 45.
Yep, 45 degrees. So if we wanted to go ahead and break this into x and y components, how would we, let's say, get the x component? We have our magnitude. How do we get the x component of this force?
It would be cosine 45 times. Or
Yep.
4.
Exactly. We have our cosine of our 45-degree angle. So it's about, well, let's call it 4.07. And we'll just multiply everything by a 10 to the minus at the end. So positive 4.07 x hat. And then what would be the component in the y direction? If we use cosine to get the x component, how do we get the y component?
It would be sine.
Yep, sine, and spoiler alert, sine of 45, same thing as cosine of 45. And so we know it's going to be the same magnitude. It's going to be 4.07 in the x hat direction, 4.07 in the y hat direction, but we do know that because it's down to the right, it's going to be negative 4.07 y hat, and then all of it times 10 to the minus 11 newtons. So we've gotten our force due to the proton acting on our alpha particle, and we've gone ahead and broken it into x and y components. So now we want to go ahead and calculate the exact same thing, but for the electron. So we want to calculate our force acting on the alpha particle due to our electron. So, exact same process. Let's first go ahead and calculate the magnitude. So, what's going to be our magnitude of the force acting on our alpha particle? Call it Fe. So, we plug everything in. It's going to be K is the same 9 times 10 to the 9. 1.6 times 10 to the minus 19. That's the same. It's the same charge as the proton, right? It's the same, plus, it's the same elementary charge. It is opposite in sign, but we're just worried about the magnitude right now. And then times our 3.2 times 10 to the minus 19 for our alpha particle. And then our distance between the two of them is going to be different, right? How do we get this difference along here, where it's 1, 2?
Pythagoreans again.
Yep, Pythagoreans again. And what is that distance? Root 5, exactly. So once again, we're going to have root 5 times 10 to the minus 9 squared, so 5 times 10 to the 18 minus 18. Plug it all in, and we get a force of 9.22 times 10 to the minus 11 newtons. Double check. Yep, it's 10 to the minus 11. So we have our magnitude of our force, and now what direction is our force going to be in? Go ahead and erase this a bit.
It's a little weird with the perspective.
I would like where it's not to scale, like with the distances.
Oh, right.
Yeah.
I mean, oriented around, like...
Here. Let me go ahead and redraw it slightly. So we have our alpha particle is going to be here. Our electron is going to be here. So we know our first force, Fp from the proton, is going to be down and to the right like this. Now, what direction is our force on the electron going to be? Remember how equal charges repel each other, and opposite charges...
Oh, right, they attract.
Exactly.
I was thinking a step ahead. I was, like, looking into the angle, like the degree.
Yep, that's going to be the next step.
Yeah.
Yep. The main thing we just want to look at here is we know that our force from our electron is going to be up and to the left. And now the angle, how do we get the angle if you're thinking about it? Let's take a look at this angle here with respect to the x-axis. We'll call it theta 2, and then we'll call this one we looked at earlier theta 1. Oh, 2. So how would we get that angle?
I did inverse tangent of 1 over 2 because the legs of the triangle that forms between
Exactly.
the electron and the particle, the alpha
Yep.
particle.
Exactly.
It would be that.
Yep. So you're going to use an inverse tangent. I'm guessing you used for inverse tangent 1/2. That would give us this angle up here, which we could use. But let's keep everything consistent. So we have our angle here, and we have our imaginary triangle. Everyone remember SOHCAHTOA. Tangent is opposite over adjacent. Our opposite here is 2. Our adjacent here is 1. So tangent of theta is going to be 2/1. So we would take the inverse tangent of 2/1. And we get an angle of about 63.4 degrees. And so then we would use this angle, multiply it by the cosine to get the x component, and sine to get the y component, right? So go down here. It's going to equal, start off with our x component. So we have our 9.22 times our cosine of our angle. We'll just throw the 10 to the minus 11 at the end again. Get about 4.12 in the x hat direction. And now, is that force going to be positive or negative 4.12? Is it in the positive x direction or the negative x direction?
It would be the negative x direction.
Yep, exactly. Up and to the left. Left is negative x. So negative 4.12 x hat. And we do the same thing to get the y component. Just the sine. And we get 8.25 y hat. And we have our 10 to the minus 11 newtons at the end. And is that positive or negative y?
That's positive y.
Yep, positive y, upwards. So we've broken down, we've got our two forces, and we've gone ahead and broken them down into x and y components. Now, why did we want to initially break them down into x and y components? It makes our next step easier, right? What do we want to do now to get the net force?
It would be vector addition.
Yep, exactly. We want to go ahead and essentially add our two vectors here, our force due to our proton and our force due to our electron, which if I want to go ahead and actually draw this to scale, it's going to be a larger force due to the electron than the proton. So we want to go ahead and add these two vectors together. And what's the easiest way to add two vectors together? So we could go ahead and draw it. So we go ahead and draw our second angle like this. Actually be more like this, realistically, if we want to draw it to scale. But mathematically, if we want it, because we can do this, we can draw a visual image, but we don't know what the values are.
Mathematically, you just add the x components together and the y components together.
Exactly. Yep. So to mathematically, we would literally, all we have to do is just add our x and y components together. So F net, we'll call it F alpha, the force acting on the alpha particle. We're going to go ahead and add our forces together. So we have about negative 0.05 x hat plus 4.18 y hat 10 to the minus 11 times 10 to the minus 11 newtons. Right? Nice and easy. Literally all we did was we add the two x components together, We add the two y components together. So now, how would we get the magnitude of this force if we want to find the actual magnitude of alpha? So before, we got our magnitude first and then broke it into x and y components. Now we're given our x and y components. How do we get the magnitude?
It would be Pythagorean. So just the x component squared and the y component squared. And then you take the square root of that.
Yep, exactly. So it'd be square root of x squared plus y squared, which, spoiler alert, because our y component is much larger than our x component, it's going to be about the same as our y component, maybe probably like we'll call it about 4.2 times 10 to the minus 11 newtons. It's going to be about the same as our y component because our y component is significantly larger than our x component. So we've gone ahead and calculated our force acting on our alpha particle. And we could also go ahead and calculate this angle as well, but no one cares about that. So now we've calculated our force. What do we want to do if we want to go ahead and calculate the acceleration of the alpha particle?
Divided by the mass of the
Yep, exactly. We're going to divide by the mass. And Zach's asking, how do we know that the alpha particle is positive? It's because what an alpha particle is it's two neutrons and two protons together. It's a helium nucleus. So two protons, two neutrons. So we know its charge is +2. We'll call it +2q, where q is the charge of a proton. And its mass, once again, as Kevin just said, to get the acceleration, we're going to want to divide by the mass. And what is the mass of our alpha particle again? Is it 3.2?
Oh wait, no.
That's the charge, right? Because that's 2 times the charge of the proton.
Right.
But the mass is 4 times the mass of the proton because we have the 2 neutrons as well. They don't have any charge, but they are masses that affect the acceleration. So our...
6.68.
Yep, sounds about right. 1.67 times 4, give it 6.68 times 10 to the minus 20. Is it 10 to the minus 26, or have we gone up 1 order of magnitude, or is it still 10 to the minus 27? Still going to be 10 to the minus 27. So, now to calculate our acceleration, we take the magnitude of our force. So it'll take about 4.2 times 10 to the minus 11 newtons. 4.2, 10 to the minus 11. And we're going to go ahead and divide by our mass, which is 6.68 times 10 to the minus 27. We get an acceleration of about 6.3 times 10 to the 15. 6.3 times 10 to the 15. And SI units for acceleration is meters per second squared, or meters times seconds to the negative 2. Anyone have any questions about this?
So far, the process is pretty alright. It's
Yeah.
just operating like a calculator.
Yeah,
I had to switch over from the ones we had to use for testing to scientific one, and then like just running through the numbers.
Yeah, exactly. Like, nothing about this process is inherently like complicated or difficult. I mean, it just gets annoying where you have to think about, okay, I calculate a value, and then I break it down into x and y components, and then I add my x and y components together, and then I take those x and y components and I put it back into a magnitude. And some people can struggle with that. It just takes some practice and, you know, doing your homework problems and, you know, preparing for the quizzes each week. You guys will get used to it pretty quickly. And plus, reality is you really only have to deal with this, you know, these super annoying examples where you're breaking down into the x and y components where it's annoying and difficult for about another week or two, because then you start getting into Gauss's law, which, you know, believe me when I say this, you might not believe me at first, it actually makes your lives easier. You know, controversial opinion. You guys will see what I mean. But, so we've gone ahead and calculated our acceleration, and once again, our acceleration is going to be in the same direction as the net force, right? So it's going to be like sort of up, pretty much straight upwards, slightly to the left. So let's go ahead and take a look at one more little example. This is, you know, sort of a bit further ahead from what you guys have touched on quite yet with Coulomb's law, but we're going to take a look at an example where we have a little electric field. It's just essentially a way to get your guys' brains thinking. This is one of the few things where you might actually be able to use some like logic and sense in this class rather than just trusting the math. So we're going to go ahead and we're going to have an electric field. We have this tunnel here, and we have an electric field that's going to go directly to the right. Let me actually color that yellow. So we have our electric field E, which is directly to the right. And we're going to go ahead and drop some particles into them. So first thing, does anyone know how does an electric field create a force on a charged particle? What's the force on a particle due to an electric field? It's for Unit 6. It's the sort of the stuff you guys will be doing this next week and also a bit tomorrow. From our formula sheet, our force on our charged particle in an electric field is going to be the charge of the particle times our actual magnitude of our electric field. And then from that, we can get our acceleration of our particle, right? It's our Q, or charge of our particle, times our electric field, divided by the mass, right? A is equal to F over M. So we're going to go ahead and have our constant electric field to the right. And we're going to go ahead and we're going to start a proton here at the top. We're going to go ahead and drop it in. So it's going to start initially traveling downward. So what is our motion of our proton going to look like? It's going to start with initial downward velocity, and it's going to enter our electric field. Is it going to go straight down? Is it going to curve off in some direction? Is it going to start going back upward? What's it going to look like? Yep, it's going to sort of just curve off to the right. Something like that. That's what our motion of our proton is going to look like. Now, let's go ahead and drop an electron into the same field. what is our motion of our electron going to look like? Let's say relative to our proton.
Down and toward the left.
Yep, down and to the left. And is it going to be the exact same as the proton but mirrored? Or is it going to take longer? Is it going to be a slower curve? Or is it going to curve much faster?
I think it would mirror.
Is that right?
I'm not sure. Because well, I was thinking the difference in masses wouldn't matter, but
Why do you think it wouldn't matter? Trying to figure out where your logic is incorrect. Explain why you think it wouldn't matter.
hold on. Yeah, but, there's acceleration, so
Exactly.
it would matter.
Yep. So,
This F equals FA.
so
It would probably curve off to the left a little harder because it has less of a mass.
exactly. Yep. So once again, our forces acting on our positive proton and our negative electron, because the charges are the same, the force is equal, just in opposite directions. But because the electron is so much lighter than the proton, it much more easily gets pushed to the side. It's like if you wanted to go ahead and drop a bowling ball in a wind tunnel, it's not really going to curve off to the side very much. Versus then if you drop like a tiny little bouncy ball or something, it's going to end up being thrown way off to the side. So our electron is going to come down. It's going to curve off to the left much faster than the proton. So now we're going to go ahead and drop an alpha particle into this electric field. So what is our motion of our alpha particle going to look like relative to our proton?
It would curve off at a slower. Wait, actually.
Would it curve off slower?
About it.
Yep, think about it.
Because if charge is like increased at a rate like by a factor of 2,
Mhm.
and then the mass is also increased by a factor of 2, you'd have to like draw out.
So it's 2q times the same E divided by our mass, which is our mass double.
It's quadruple.
Quadruple, exactly. So we have 4 times the mass. So that means our acceleration here is going to be,
Much less.
well, it's going to be less. It's going to be about half as much.
Half as much. Yep.
Yep, so it's going to come down, and because alpha particles are positive, it's going to curve off to the right, but at a slower rate. It's going to curve off. Sorry, at a slower rate than our proton. So it's going to come down, and it's going to curve off much later than our proton. Sorry for my visualizations. Let me draw it over here. So it's going to come down. It's going to look something like that. Running out of room at the bottom. But so because its charge is twice as much, so it's twice as much force, but it's 4 times as much mass. So the acceleration and how much it ends up curving in quotation marks, is going to be half as much. So it's going to curve slower. That's sort of, a sort of nice little way to sort of visualize how electric fields are going to affect things. And so we have our protons and our electrons, which same force, much different, significantly different masses. So the electron's going to curve much quicker. And then our alpha particle, it's twice as much force, but 4 times as much mass, so it's going to curve slower. Anyone have any questions about this? Anyone feeling still a little unsure about Coulomb's law or electric forces or electric fields? All right. Well, if that's the case, I'm going to go ahead and wrap up our session here just a few minutes early. we'll be having another session tomorrow, more on Unit 6, which is going to be like electric fields and forces due to electric fields, and sort of like line charges and stuff like that. It's going to be really fun. So same time tomorrow, 1 to 2:15, and sort of get you guys ready for your quiz on Friday. And once again, if you have any questions, feel free to ask me. Ping me in the Discord or message me, or post your questions in the class questions chat, and people generally get to you. All right, have a good day, guys. Thanks for coming.
Thank you.
Thanks.
Mm-hmm.